So I actually came up with a little bit better title, Solar Insulation Micro Forecast to Integrate PV Power Plants with Today's Electric Grid. And I'm just going to go over what's going on with the electrical industry, the solar electrical industry, and why there really hasn't been a whole lot of adoption of solar so far, and what some of the technical challenges are to overcome. So first off, this is our research team. I'm up there, Dr. Anthony Menicucci. We had Dr. Andrea Mamoli. He used to be a professor down here at UNM, but he actually went off to EPRI, which is the Electric Power Research Institute. And Tom Caudell is our AI specialist that we have been working with. And so we've had an STTR, phase 1, and a proof of concept with 2 issued patents and 75 fielded hours of our solar irradiance micro forecasting apparatus. And you can see it right here on the bottom. I'm going to minimize, hide the thumbnail view. So we predict incoming clouds and outgoing clouds over solar panels within 10 minutes. That's interesting there. Just note a picture containing outdoor boat, plane sitting, description automatically generated. That's interesting from my PowerPoint. Anyway, my AI presentation goes over that, so I'd recommend you go see that. But let's get back to solar irradiance micro forecasting. So we have incoming clouds over solar panels, and what we're trying to do is we're trying to make a 10-minute prediction or less of when that power goes onto or off of the grid. Basically, when you have a cloud that comes by, you have this intermittent power, especially if you don't have any storage at your PV site. And storage is still expensive. So when you add storage, your PV site, your PV generation becomes quite a bit more expensive. But basically, the electrical grid operators have to keep their voltage supplied to their customers between a specific range. So you can't go too high and you can't go too low. And when you have solar panels and solar farms out there that are occluded with these clouds, they turn on and off extremely fast. So what we want to do is control the derivative of power that goes out. So the electrical grid can handle a certain amount of changing power. It can absorb some change if people turn on their load or turn on their house air conditioner or something. You're going to need more power, you're going to need less power. So power is always changing. But as the power changes, the electrical company has to make that power up. So if people start using more power, then you're going to have to make that up. If you use less power, then you're also going to have to turn down how much power you're generating on the grid. And it takes a while to adjust. And that's the whole point of giving a little bit of a heads up with these forecasts. And so we could see here, this is just a little simulation. I go through this in my other presentation, but you can see that if we don't have any storage at all, the second derivative in terms of kilowatts per minute that go out to the grid can actually be very significant. And if you're always playing catch up or you're behind and your power equipment can't react fast enough, then you can actually damage your power equipment because it's always catching up. And also you can't have too much electricity or too little electricity on the grid because you'll have voltage problems. And that causes a whole host of regulatory issues. So by adding forecasting and a smoothing battery, like a flywheel, which I'll talk about in a second, we can use 27% less capacity. And we could also have 33% less battery wear and tear. So there's a direct market potential for making sure that if you do have storage, you don't utilize your storage as often as you would when clouds are out, or as when you don't have a solar forecasting. So we've also discovered that you can reduce the onload or the grid onload tap changer operations. And let me go over that right now. So this is a GE turbine, and this is a natural gas turbine. This actually makes up the power. So when people turn on or off their load, or a cloud comes over a solar panel and then passes, this huge gas turbine, natural gas turbine, not this particular one, but something like this at P&M has to turn up and turn down. So they have to match the output. And you can see the manufacturer specifies 68 megawatts per minute is your maximum ramp rate. Well, if you've got a large solar field, sometimes your solar field could turn on or off faster than that 68 watts per minute. And that also doesn't include the other loads. So what happens in between with these tap changers? Well, tap changers are just it's a double coil on both sides. And then instead of having one transformer that is connected, you have multiple taps on the low voltage side of your transformer. And so if a cloud comes over, and this is an example of a large piece of equipment, these are hundreds of thousands of dollars, they can go up to millions of dollars. But when clouds move over, your tap changer is going to change positions to make sure that the voltage on the grid stays relatively constant. And so inside here, there's a rotating chamber that's going to rotate around. It's going to select a different one of these tap changing positions to make sure that the grid, there's not too much electricity and there's not too little electricity on the grid. So to summarize what happens, we have this intermittent solar field, and it produces this really bad PV power. It goes up and down, there's lots of clouds. And basically, that poor power is given to a tap changer before it goes to your customer. Right? And there's actually a natural gas generation in the middle. But the amount of tap changing positions that you have when you give this poor quality power through your tap changer overuses the tap changer. And what we're doing with our research is trying to use a flywheel or other energy storage unit, which is a flywheel. This flywheel energy storage unit from Beacon Power is extremely high power, but low energy. So it can discharge a very large amount of energy of power, but the energy is only about 4 minutes. So it only lasts for about 4 minutes. But that's all you need to be able to smooth your power out. And then as your tap changer interacts with the smooth power output, you have much less tap changings while you allow your natural gas turbines to catch up. So what's a little bit different from some of our competition? There are a few companies trying to do this, one in Australia, and then there's also another one, UCSD has some research going, but we're trying to get an actual product out. In fact, I'm actually thinking about trying to sell the entire field, where the field is derivative controlled on the power end. So the amount of power that goes out is relatively constant, no matter what kind of cloud cover you have. I mean, other than longer than 10 minutes. Obviously, if it's totally cloudy, you're going to have to use your natural gas generation, but it's already installed. So this is a way to install solar right now that's also cost effective. So we use different sensors that just came onto the market a little while ago. We also use an AI called adaptive resonance theory, which is where I get all my AI experience. So I had to get up to speed on that. We use lap art also. It's a little bit different. It converges very fast, and well, it's very fast in processing, and it converges very fast. So we were able to accurately predict irradiance within solar fields within about 2 minutes, and we're actively pushing on to a little bit longer time frames. So our phased, we did a phased investment. We've completed our first NSF STTR, and we're actively looking for other research right now. I think we're a little bit too we're not quite ready for investment funding. We're still in the research stage, but we're looking for an STTR phase 2 right now, or any other research funding right now. But that is about it. So again, if you have any questions, you can reach out to me. My number's here. And then also, I put on my website here. So there's a technical presentation, and then we've got a marketing presentation. So thank you so much. I appreciate it. And I will turn it back now.